Hello, this is Physics Lab 2, motion of a falling object. The purpose of this lab is to observe the motion of some object that is dropped from rest while falling relatively slowly. And we want to consider forces such as drag and gravity while the object is falling. We also want to compare a model of the falling object that considers gravity to one that considers both gravity and drag. So we can see how drag influences the ball as it falls. Some of the assumptions we're making is that we're only going to be observing displacement along the y-axis and that down is a negative y direction. We also going to see that average velocity will be equal to the final velocity because terminal velocity is hit whenever f net is non-constant. So we expect to see that the model accounting for drag is more realistic than its counterpart. That's what we kind of hypothesize to see, and we'll see if that's true. So some of the fundamental principles of this lab include Newton's second law and some of the forces that we'll get into. So Newton's second law, also known as the momentum principle, basically says that the rate of change of momentum of a body over time is directly proportional to the force applied. And the forces involved in this lab are drag and gravity. So drag is proportional to velocity squared, and it opposes the direction of a moving object. So if object is falling down, drag will be pointing up against gravity. And the force of gravity is that's calculated using this formula is equal to 9.81 meters per second squared. We also have the position and velocity update formulas, which basically allows us to predict the future position velocity of object given some initial information, which we'll be using in computation models. So the experimental setup, we have a spherical object that is dropped. We're going to choose an orange that acts as the system. The surroundings are anything external to the system. So forces such as drag and gravity will be the surroundings. For its drop, the position will be at 0 meters just before I drop it. The initial velocity would always, of course, will be also 0 meters per second. And the orange's mass is about 0.0868 kilograms. And for glow script, we want to consider a model using only gravity and one that considers gravity and drag. And this little free body diagram just kind of shows what happens as the object falls. Um, as it falls, air drag force starts to increase as the object speeds up. And as the object speeds up, sooner or later, drag force will cancel out the force of gravity and terminal velocity is hit. So no acceleration, the ball will be falling at a constant speed and that force will be 0. So here's a video, the tracker video of me dropping the orange. As you can see, the y-axis is pointing down. So as the ball of orange is dropped, we see that it's going farther and farther down the negative y-axis. I also use a tracker every other frame, so you can see you kind of get a better visual of how the orange falls as it hits the floor. And as you can see, we have a little bit of like a exponential downward slope happening right here. So that is what tracker shows us. And these are the initial condition of computation model. Of course, position, velocity, and the size of each time step. We also have the ball's mass for 0.068 meters per second, or sorry, kilograms. And this is the first model that considers only gravity. So when it considers only gravity, we have the gravitational force formula, but F drag is equal to 0, 0, 0 because we don't want to consider that. So we only have gravitational force affecting the ball. We also have the velocity update formula and position update formulas, as you can see here. And this is the graph this is how the graph looks whenever we're only considering gravity. When we're considering drag as well, and drag is proportional to velocity squared, you can see here F drag is no longer just a 0 vector. We actually have this formula that considers the magnitude of velocity squared because we know that it's proportional to the square of the velocity. And as you can see here, we also use the same velocity update position update formulas, but now the graph looks a little bit more different when we consider drag. And in the end, when we graph these things out, as you can see, all three graphs, the tracker one and both of the models, start out relatively the same, but sooner or later, the the tracker one, which is more realistic, and the yellow one that considers gravity and drag, they start to kind of meet each other in the middle because they're a little bit more accurate than the red graph, which only considered gravity. So it looks like the computational model with gravity and drag is a lot more closer to real life than the computational model without gravity, with only gravity, sorry. And some of the errors that could have been considered in this lab is human error. So I may have dropped the ball slightly to the side. The camera quality could have been a little weird, so tracker could have messed up a little. The ball also could have tilted as it fell, or the orange could have tilted as it fell. And there could also have been some glow stripe errors, such as any wrong inputs and wrong calibration. And some surrounding forces, such as AC in the room, could have also affected. And which model better predicts a terminal velocity? It would be the one that considers gravity and drag, because this model illustrates the velocity is decreasing over time. It implies that drag force and gravitational force will eventually cancel out, resulting in a net force of 0 units. And if the object was initially thrown downward, the terminal velocity would still be the same as the case where the object was dropped from rest, because terminal velocity is not dependent on initial velocity. It is, however, it will be reached at an earlier time as the ball will experience a greater drag force that will more quickly cancel out the force of gravity to achieve zero acceleration. So same terminal velocity will be achieved, but just at an earlier time.